Welcome to qnawire.
In this problem, we are given a weight that is hanging off of a string, but with two opposing forces acting on the string at different points. We have F2 and F1 here, and this angle is 45 degrees. And we know that this has some weight W. So we have the tension and a few different parts of the rope here, which we're going to try to break down and analyze, because we want, in the first part, it asks us to find the tension along the diagonal part of the string. And then in the second part, we're going to find the magnitudes of the two forces. So let's draw our free body diagrams at our different points of intersection here. So in our first one, we just have T1 pointed upwards and weight of our object pointed down. In our second free body diagram, we have F2 pointed to the right, T2 pointed diagonally to the left, and T1 pointed directly downwards. Then in our third free body diagram, we have T3 pointed directly up, F1 directly to the left, and T2 now pointing downwards to the right diagonally. So in order to solve Newton's second law equations, let's break this down into components, and let's move into the reference frame where two of our forces are already perpendicular with each other. So in both of these reference frames, I'm going to break it down using the following reference frame. So yeah, both of these at a 45-degree angle with the horizontal or vertical in this case. So when we break it down into components, we have T2 cosine of 45 degrees, F2, T1, and then opposing T2, F2, we have T2 times sine of 45 degrees. And our other force body diagram here is going to look pretty similar. Just looks like it's actually been flipped over and rotated. So we have T2 cosine of 45 now pointed down, and T2 sine of 45 now pointed to the right. So if we look here and set up our Newton's law of second equations going down our force body diagrams, in the first one we have just T1 minus W equals 0. And so that means T1 is equal to W. And the second free body diagram, we get from the vertical components that T2 cosine of 45 degrees is minus T1 is equal to 0. And then since we're interested in T2, we can solve for that and substitute in a value for T1. Let me save myself writing cosine of 45 degrees twice and just do that now. And so plugging in the appropriate value for our weight here, which we're given is 60 newtons, we find that the tension along the diagonal part of the string, which we have labeled T2, is 84.9 newtons. Now, and that is the answer to our part A. Part B asks us to find the magnitude of the two forces. So these two forces show up in the horizontal components of our equation. So we see that F2 minus T2 sine of 45 degrees is equal to 0. So F2 equals T2 sine of 45 degrees. And we can substitute in T2. So we had W and then the sine of 45 divided by cosine of 45. So that would just be the tangent of 45 degrees, which is equal to 1. So F2 would just be equal to W, which is 60 newtons. And we'll see that F1 is going to have to be equal to F2 here, since they're both going to be equal to T2 sine of 45 degrees. So F1 equals T2 sine of 45 degrees, which is equal to F2, which equals 60 newtons. So we have equal and opposite forces opposing on this. And just to do a mental check, we can think of treating this object as one big object here acting on this string hanging from the ceiling. So it has F2, F1, T3, and W. So we found that F1 and F2 are of equal magnitudes and they're in opposing directions, so those cancel out, so there will be no motion there. And then let's see what we would find for what T3 tension would be equal to here. And we see from our Newton's second law equation that T3 minus T2 cosine of 45 degrees is equal to 0. So it's T3 equals T2 times the cosine of 45 degrees. And we see that T2 is W divided by the cosine of 45 degrees. So T3 is just equal to W. So these are equal opposing forces. So that means there will be no motion in this object system.